Let's take a look at another circuit configuration and see how the root 3 will be applied properly here. So in this instance, we will have a Y-connected source on a 3-phase circuit feeding a single-phase load. And just like on our last problem, we'll just keep it simple and solve for power at the load. Now, when we say single-phase load on a 3-phase system, you should be asking yourself, is this connected line to line or line to neutral? Now, let's say our particular problem is line to neutral. And to contrast that, just to make sure we're clear, let me show you a line-to-line example. So, line-to-line connection would look something like this. Very obvious seeing the difference between line and neutral connection there. A quick thing to remember here is that line-to-line values are the larger ones, and line-to-neutral values are the smaller ones. And what I mean by that is this. If line-to-line would equal 480 volts, which is very common, then line-to-neutral would equal 277 volts. And we see very easily that these two values are at a difference of root 3. Another common one, very obvious, is 208 volt line-to-line, with 120 volt being line-to-neutral. Yet again, a factor of root 3 in between. We all know this. I know that this is very basic stuff, but I just want to be clear, so that's why I'm saying this. Another obvious thing to make sure we're all on the same page about is the way these things are written and the way they're spoken about. Line to line can be notated with all of these options. And line to neutral can be notated with all of these options. Saying line to line or line to neutral can at times be a mouthful, as I'm struggling with already. So often they're just called line and phase. And sometimes, and probably inappropriately, they're called just line and neutral. But to keep those distinguished, we're going to try and keep consistent here with line and phase, or line to line and line to neutral. Okay, enough of that. Let's move to the particular factors involved for us to be able to solve for power at the load. As in our previous video, we discussed the 3 factors necessary to be able to work with the root 3 with these particular types of equations. If you recall, the first factor is what is the source. And here it's obvious we've said we have a Y source. The second factor is what is the load. And here we have a single-phase load, and it's on a 3-phase system, but we have a single-phase load, and it's connected line to neutral, as we've been discussing. The third factor are the givens for this circuit, and let's supply them here. We'll say that we have a 35 amp line current, and we have 12.5 kV line voltage. Okay, a good way to see that phase current matches the line current is to notice that the current is not diverted by any other branch along the way to the load. In our last example, it was very clear that the phase voltage and the line voltage match, and now we're dealing with the current in this particular situation. And with this Y connection, it can be maybe a little confusing to see that, so a good way to help visualize that the phase voltage, or rather the phase current and the line current match, is to visualize it in opposition to the way a delta connection might look. When we see a delta connection, we can see that the current can be diverted in one of 2 ways en route to the load. So I'm just going to give you a quick example of what that would look like here. So you see on the source, the current traveling to the load can be split off in one direction or the other. And so that's a more uncertain circumstance than what we're dealing with here. So with phase current being provided, we know that, or rather with line current being provided, we know that we have a matching phase current as well. So, we're solving for power at the load. Now remember, like the previous video, we will still employ the root 3 factor in the formula. But here the key is, where's the root 3 coming from? Before, in our previous video, it was coming from the current. Now, it's coming from the voltage. Okay, but back to our problem in question. Because the load is connected line to neutral, we need the phase voltage. Now recall what we just said about what these connections are called. Line to neutral connections are called phase connections. So this means we need to convert the given line voltage to phase voltage. And from our last video, we saw that line values are the larger values, while the phase values are the smaller ones. So this indicates to us that we must divide by root 3 to get the smaller value. Here, we're moving from large to small. This is the most important thing you can understand about using the root 3 from these videos. You can't just stick a root 3 on the end of your formula and expect to get the correct answer every time. So, starting with the general power formula, let's substitute in the correct variables with the root 3 that we've been talking about. And then we can apply the given numbers of our problem so that we can do the calculation. Here, make sure and watch out for the kilos and the megas of your givens. Remember, we've got 12.5 kilovolts, so that's why that's there. And the rest of the equation is pretty easy. You can just plug into your calculator and get the answer. And, as Dennis Reynolds says, boom.